Lesson 20.1, Task 2. Choose among linear, exponential, and quadratic models. Choose a quadratic model. Previously, you saw that when regression is used to fit a quadratic function to a data set, the coefficient of determination, r squared, indicates how well the function fits the data. A coefficient of determination can also be generated when you use regression to fit linear and exponential functions to data. For linear and exponential functions, the coefficient of determination equals the square of the correlation coefficient r. That is capital R squared, that's our correlation of determination, equals lowercase r, which is the correlation coefficient squared. So those two will be equal. If a linear, exponential, and quadratic function are each fit to the same data set, you can compare the values of r squared for the functions to help you decide which function model the data best. In general, the closer r squared is to 1, the best the function fits the data. A study found that the average fuel economy for a sample of cars varied by driving speed as shown in the table. Find a function that models the data well. Then use the function to predict the average fuel economy for a driving speed of 60 miles per hour. All right, so we're going to use the calculator to do this. So remember, if you go to Stat and Edit, it's going to allow you to enter the data. So I'm going to pause the video just long enough to enter the data, and that'll save a little time, and then we'll look at what it shows us. Okay, so now I have the data entered in my calculator, in my table here, and that came straight from the table. We put our x's in L1 and our y's in L2. So it says make a scatter plot of the data and use regression to find a good model. Okay, so now this time we have to change our x's in our table. So we can see that it goes from 15 to 75 and 24 to 24. So these don't vary a whole lot. It goes up in the 30s, but back down to 24. So we're going to go from 15 to 75. So if I hit graph, I'm not going to see anything. That's because I need to change my window to fit this data. So my x's, I still don't need negative, so -2 is fine. But I do need to go up to past 75. So let's go up to about 80. So this time let's use a scale of 5 5 should be pretty good. All right, and then let's change our y minimums don't have any negatives, so we'll start at -2. This does have to be a negative number. That's the only reason I don't enter 0 here. If you put a 0, it'll say error or something. So you do have to put at least -1 or -2. All right, so your maximum value, you can see that it goes up in the mid or lower to mid 30s. So let's put 35 here. And then let's go to a scale of, let's do a scale of 5 as well. All right, so now when we hit enter or graph, we can see the points that we put in there. All right, so it's definitely not a line, so it's not linear. It's not exponential growth or exponential decay. It kind of looks like it's not perfect, but it kind of looks like an upside down U, which would be a quadratic function, a parabola. So just looking at the points, I'm going to say it's probably a quadratic model. But we're going to look at all three to see which one is the best model. So it says make a scatter plot of the data and use regression to find a good model. Enter the data pairs into a graphing calculator and make a scatter plot. So we've done that. The data points rise and then fall, which suggest a quadratic model. The coefficient of determination for a quadratic model, r squared, is about 0.919. Is also reasonably close to 1. So it's not as good as the last task where it was like 0.999, but 0.94, I mean, that's a pretty good, pretty high number, close to 1. And so a good model for the data is this. So if we were to use our calculator, we can go y equals, well, I should have went to stat first, but I'm going to do calculate. and I'm going to do number 5, which is quadratic model. And my calculator will now write an equation. You can see the r squared here, the 0.9419, 0.94186, because 6 is greater than 5. This rounds up to a 9. So this is this function right here. Okay? If I want to graph it, I can do that as well. I can go to vars, 5, equation, hit enter, and then graph, and it's going to graph. And you can see visually how that model kind of hits most of those points. It's not perfect, but again, 0.9419, that's a pretty good model for most cases. All right, so they have graphed it as well. So now it says predict the average fuel economy for driving speed. All right, so predict the average fuel economy for a driving speed of 60 miles per hour. Find the value of y when x equals 60. So all we have to do is take the equation that we got using our calculator and plug 60 in for x and solve. When they do that, they got about 30.6. The average fuel economy for a speed of 60 miles per hour is about 30.6 miles per gallon. All right, it says use the regression of a graphing calculator to find the linear function and an exponential function that models the data. Enter the coefficient of determination, that's the r squared, for each function to the nearest hundredth. All right, so we've already got our set of data in there. So we're going to clear this, and now we're going to go stat, calculate, and we're going to do a linear regression. So number 4. Enter through that. So it gives us our A, our B, our R squared, and our R. So R squared, it says 2.22. Now if you stop here, you're going to think, well, that's weird. We want to know if it's closer to 0 or 1, and this is above 2. But if you come all the way out here to the end, you're going to see this e to the -5. So this is in exponential form. This is in scientific notation, which means I've got to move to the left 5 places. So if I move this decimal 5 places, I'm going to go around the 2, which is 1, and then I'm going to add 4 zeros and then put my decimal there. So this is very close to 0, which means it's not a good model because we want a model that's close to 1. But just looking at the graph earlier, we could tell that it did not look like a line. So we could kind of assume that was the case. But that just kind of, that makes it even more real when you check it using the calculator. Let's find the exponential model. All right, exponential regression. All right, and we've got our A, our B, our R squared, and our R. So we're going to look at our R squared. And again, we've got 1.5, and we look at that, and it's greater than 1. But if you come all the way out here, this is going to be moved to the left 7 places. So it's going to move around the 1. That's 1 decimal place. Then you're going to add 6 zeros and put the decimal in front of that. So this one is even closer to a 0 than the other one. So it says, do the values of r squared support the conclusion that a quadratic model is best? Yes, because both of these were close to 0. And for the quadratic model, remember it was 0.94, which is much closer to 1. So that does support the information. All right, so a value of r squared is closest to 1 for your quadratic model or your quadratic function. So the values of r squared support the conclusion that the quadratic is the best fit. All right, according to the quadratic model, what driving speed maximizes fuel economy? All right, so if you look at the model again, we can see the data here. You can look somewhere around probably 40 to 45. So you can say about 45 miles per hour is when you maximize your fuel economy. So anytime you have a quadratic equation, remember your maximum comes from the vertex. So we don't have an exact number here, but you can tell it's somewhere around 45 there to be a good estimate. All right, that is all for task 2. If you have any questions, let me know.